So now we're going to talk about the atmosphere's planetary circulation. All right, this is instead of looking at what is my weather at my house going to be, we're going to look at the globe as a whole. So you've learned a lot about different variables and how they interact in the weather to make the weather. Well, let's make the assumption that all we care about is if I have a spaceship that's circling the Earth and I just want to know what earthly weather's like. I'm from outer space somewhere. I don't know. And that is what we're going to be talking about. What is our whole world's weather like? So we'll move forward here quickly. Think about it. If the Earth didn't rotate, you'd have one side that was always facing the sun, one side that wasn't. You'd have a pretty simple, straightforward circulation. The Earth does. So with that rotation, what we wind up with is basically three belts of winds in the northern hemisphere and three in the southern hemisphere. They're right here. The westerlies, where we live, between 30 and 60 degrees north. The polar easterlies, there's an easterlies also down around just north of the equator. And then you just have everything same way down in the southern hemisphere. With that, you have basically four areas really of different pressures. You have low pressure that's always going to be near the equator or where the sun's the strongest. You have high pressure around 30 degrees north, low pressure around 60 degrees north, and near the poles we actually kind of tend to have a little bit more high pressure. Here is an actual surface weather map. Take a look at it. If you were to think about January, sun's down in the southern hemisphere, right? So everything should be shifted south. We have high pressures a little further south, and our high pressure off the east coast of the United States is a little further south. The lows are a little further south. Everything shifted southward. In the summertime, everything shifts back to the north. So, but notice, if you average the weather over these months, you get a pattern very close to what we talked about. So, with that, we have subtropical, anticyclone. These are big areas of high pressure that cover large parts of the globe. There's ones typically around 30 and 60 degrees north, and we can get some over other areas of the world as well. They're where our air masses kind of originate. These have light winds, so they pick up what the ground under them is like, and they cause the weather, the air mass, to become similar to the ground. So if I have a big high pressure over Canada, sitting over a dry, especially in the wintertime with the snow cover, very cold air. So that is where your cold air is coming from. Say I have a high pressure that develops over the desert southwest of the U.S. What do I get there? Well, I have not much water, so it's going to be dry. It's going to be hot, so I have a dry, hot air mass. You see where I'm going with this? Now we have some winds that have those polar highs, polar lows, and with that, we get a wind pattern, especially aloft. Think about it in the westerlies. I'm telling you, the westerlies are going to flow from the west to the east, what they're called westerlies for. So where we live, most of our weather originates to our west and flows to the east. So what is happening in California? Eventually, it may be impacting your area, maybe changing as it's coming across, but that same system is going to play a role in weather at your house over West Virginia or that area. So you can see how they're wavy. The atmosphere is much like a wave in the flow pattern. We talked about different pressure gradients and influences on moving the wind. Well, here's a classic geostrophic wind flow where they're flowing right along, caused by the pressure gradient and with the tropopause. Cold air compresses. So north toward the poles, the air is going to be compressed down. and the tropopause is going to be lower. Down towards the tropic, it's going to be much higher because the air is expanded, hotter, less dense. In between, where we're constantly changing from a polar air mass to a warm air mass, the tropopause will go up and down a lot. And there's a trade wind inversion that impacts the sinking over the middle of the Atlantic. For example, around 30 degrees north, we have sinking winds. We have winds that are coming from the east to the west. That's how Columbus came to the United States, by following that wind flow. That sinking causes warming aloft, the cooler ocean. We wind up in inversion. We don't get as much precip. Kind of a sunny area. Intertropical convergence zone. Basically, it is going to form where the air temperature is the hottest. The air temperature is the hottest. The air temperature causes the density to be the lowest. That is where an area of low pressure is going to tend to be. Air is going to want to flow into that low pressure, as we know. So what happens? Well, in July, our summer means the sun is fairly far north. What you get over the oceans is, it doesn't move a whole lot. Remember, it takes a lot of heat to warm up the ocean. So the intertropical convergence zone moves a little bit north in the summer, a little bit south in the winter over the oceans. Now, look at over a continent, like over Africa or over Asia. Notice how that air heats up a lot more over the continent, moves the intertropical convergence zone much further north or south, depending on the season. Think about the wind flow now. If you were in India, you would get the flow from the south in the summertime, in July. What's to your south? The big ocean. In the wintertime, where's your flow coming from? The north, heading into the intertropical convergence zone. What's to the north? Very dry mountains, cold. So you're going to be very dry and cool. You see how the intertropical convergence zone creates these wind flows. These wind flows, because they persist for months at a time, are called monsoons. And here you can see them. All right, another part of the climate. Let's think about Charleston, South Carolina versus San Diego, California. They're at exactly the same latitude. Very different weather patterns. San Diego has a big high pressure system that's centered out over the Pacific. The wind is coming from the north to San Diego, over the water, down along there, but they're still getting plenty of heating. And intertropical convergence zone in the summertime is pushed a little bit further south, so they're even more under that high. With that being said, that high pressure to the west and southwest of them in the summertime is sinking motion on that side of it. Very dry conditions. In the wintertime, they're moving up. The high has moved back to the south a little bit, back to the north a little bit, and maybe allow some winds to come in from the west. Charleston, on the other hand, winds from the south, lots of unstable, humid air. What do you get? The biggest rainfalls in the summertime. All because of those highs. And with those highs being permanent features pretty much, they influence the flow in the ocean. Think about our Gulf Stream that off the east coast of the United States comes out from the Gulf of Mexico up along the east coast and eventually heads over to Europe. It keeps everything warmer on the east coast because it's pulling warm air up along the east coast of the United States. Why is that happening? We have the big high sitting over the Atlantic, southerly flow there, pulling up warmer air. If you went in the Pacific Ocean, what do you get? Cold. Water's cold, but coming out of the north along California and all. So it's cooler there. Keeps it cooler in the summertime there. We actually have a monsoon in the United States called the Southwest Monsoon. This occurs because air is heated over the tropics of the mountains in Mexico Arizona, that area. When it's heated, it expands, creates low pressure at the surface. Pressure falls slower in the vertical, so you have high pressure aloft. It becomes pretty stationary. Think about it. If you have that pattern, then you're going to be pulling air in either from the Gulf of Mexico or the Pacific Ocean into that area. That hot air is going to rise. You wind up with thunderstorms, and then the air circulates back out. See, that is their time of year to get the most rainfall in the desert. Rossby waves. If you looked at a 500 millibar or 300 millibar chart, I showed you the wave pattern. Well, in that wave pattern typically are 2 to 5 what we call long waves or Rossby waves. They are where these little tinier short waves kind of intensify. And this is kind of confusing, I know. But they're going to, if you looked at a weather map, you would see an area where you have a pretty broad low pressure sinking down into one part of the world and then back up into another. And you best look at this from the poles. If you look down from the poles, you can basically see 3 or 4 of these. And if you looked at them with a time lapse, they're not changing a whole lot over the course of a week or two. Over longer periods, they may move from one part of the country to the other. That's why when they occur, for example, in the western United States, it gets cold in the west, a big ridge of high pressure tends to develop in the eastern part. Currently, what's happening, as a matter of fact, what you wind up with is cold west, maybe some rain or snow, warm east, dry weather. And here you can see them. Now, the flow pattern can be either zonal or meridional. Notice there is a wave to the zonal pattern, but it's much faster. And guess what? During La Nina, which is what we have now, we have a lot of zonal type flows, weak zonal type flows sometimes. So be interested to see how this winter develops. But with that, if a zonal flow occurs, you don't get lots of cold air coming south or lots of warm air coming north. So the temperature contrast is not as sharp. There may be some, and they're going to move fast. In other words, if I have a cold front that pushes into the Rocky Mountain area, it's going to tend to fly to the East Coast in a couple of days with the zonal pattern. Won't be as cold as some of the other ones might be. Now, if I have a meridional, it may take 3 or 4 days for that same front to make it to the East Coast, but it's going to be much warmer ahead of it, much colder behind it. You can also get blocking patterns where the flow basically is moving along and just can't go anywhere. It's blocked. These cause extreme flooding. They also cause really warm or cold air for long extended periods of time. Here was a pattern that developed in 93, had lots of moisture coming up into the Midwest in the spring and early summer, and you prevented tremendous rainfall, flooded the Mississippi River and a lot of that area because the pattern just locked in there. Sometimes it locks in different locations. Right now, we're locked in pretty much over our area in the eastern part of the country with high pressure. It's just sitting here. That's why we're getting a lot of drought conditions. You notice a difference in rainfall, too, with that. All right, jet streams are going to be developing. Remember, the greatest contrast in pressure is going to occur where there's the most change in temperature. The most change in temperature occurs in the upper atmosphere. It takes a while for the pressure to change as you're going up if you're under high pressure. If you're under warm air, remember the pressure drops slower. But under cold air, the pressure is dropping fairly quickly. So you create this strong pressure gradient in the upper atmosphere, and that is where the jet stream formed. It's all due to this temperature change. That is why if you looked where the jet stream is, to the north of it, you're going to typically find the coldest air. To the south of it, you're going to find the warmest. One of those jet streaks and find where the cold front is. They shift as well. During the summertime, the jet stream is going to be further north, maybe up over northern United States, maybe even staying in Canada. In the summertime, it'll flip down across the United States. There are little jet streaks that ripple through this. Basically, they're areas of the stronger winds. With that in mind, they induce divergence in one part of the flow and convergence in another. If I have divergence aloft, what happens? I am going to lift air from aloft and from the ground up. Low pressure is going to develop at the ground. If that is the case, if I'm developing low pressure there, I'm getting convergence at the ground. Air rising cools, right? The cooling air produces precipitation and low pressure. And there you can see the pattern. And here is where the areas of divergence and convergence are on the jet streak. Upper left in the front, right rear. Sometimes you can get a second jet streak that might be coming like this. And upper front, right rear might correspond, and you increase the divergence, you get a stronger low pressure. All right. As part of the global circulation, we have things like El Nino and La Nina. We also have a historical trend of those as well. You can see how they vary. And we also talk about the Ekman spiral here a little bit. If you're along the east coast of the United States, I'll take that as an example. If I have a southwest wind moving the water to the northeast, typical Gulf Stream motion, that water is going to want to turn with the Coriolis effect. So it wants to turn outward, away from the area. So it begins to turn out at the upper levels. As it turns out, what happens is the water below it begins to rise up, and you create literally a spiral, cooling the water near the coast. So El Nino and La Nina impact the globe. Think about the Pacific Ocean. It covers a large area. So if we have a warm phase, or El Nino, the Pacific is warmer than normal, creates lots of thunderstorms, heats it up, air is rising there, it produces stronger wind flow into that area, and we wind up with stronger flow of air. La Nina, not as much rising of air, and therefore not as much power to the winds. There's a North Atlantic oscillation. Every one of these, I want to just looking at quickly here, basically is showing you global averages of something that impacts our area. So here's a United States analysis over the globe. Look at 60 degrees north, which would just be right across Greenland, south of Greenland there, northern Canada. You'll see lots and lots of low pressure. 30 degrees north, you see lots and lots of high pressure. Towards the poles, you see lots of low pressure and then into high. And you can also see the intertropical convergence zone there, moving across the southern parts of Central Africa and all. So this is a classic look at the global planetary circulations. So I wanted to take a quick peek here. Take a look at winter outlook. The winter outlook was based on obviously numerical model forecast, but also the fact that it's going to be a somewhat of a La Nina pattern. La Nina means the ocean in the Pacific is a little bit colder than normal. With that, what it does to the pattern in our weather for the American country is it produces less of a contrast in temperature across the country, but we wind up with slightly above normal to the south. More sunshine occurs, so we get a little bit warmer. less sunshine occurs to the north, so it gets a little bit colder. So that is why we wind up with a map that shows a little bit warmer temperatures on average across the south. Also, less precip across the south as well. So it's going to allow more drought to occur in the south. We cover more of the area with drought. Here you can see the precip. Most of the precip is coming in across the north, less into the south. So here is a current, for example, map of the drought conditions across the United States. Well, if we take what we just noticed, what you would expect is the droughts across the south to worsen and expand. The one we have here in West Virginia right now that's actually extreme in some areas may actually get worse because more of the precip is moving to our north. Now, the northern ones may become less with time. So this kind of a forecast with La Nina gives you an idea of how the pattern long-term impacts our weather. And with that as well is here is an Arctic oscillation. Arctic oscillation, think about it, there's a big upper low sitting over the poles. If that upper low gets strong enough, what happens is it can't let any of the cold air out. It just keeps it right there. If it gets weaker, more of the cold air can come out. So when the Arctic oscillation is positive, cold air ain't just not going to come out of Canada and north that much Arctic air. Now, if it gets very weak, you tend to get a whole lot more Arctic air coming out of Canada into the United States. So it's a great tool, this index, for forecasting that, oh, we may have an Arctic outbreak in the United States somewhere. So the North American oscillation is just another depiction. What we're looking at is the high pressure that we know is around 30 degrees north versus low pressure that's around 60 degrees north over Iceland. The change in that pressure gradient changes the wind flow. It means one is either stronger or weaker than the other. And when that happens, that impacts weather in the eastern part of the United States. So interesting how all of this interplays so you can see our global weather. In other words, if somebody wanted to look at the globe, they're getting a picture of it. We're not looking at local weather as much. We're looking at globe. So I hope you got something out of this. Let me know if you have questions.